Okay, let's talk about section 13.4. Mathematical Induction. Uh, what is a mathematical induction? Let's start from an example. For example, we have a statement. 2n is always an even integer. Okay, so this is one statement. This statement actually contains infinitely many statements. When n is a 1, you say 2 is an even integer. When n is 2, it's a 4 is an even integer. When n is 3, it's a 6 is an even integer. So this should be proved for all natural numbers. Okay, so it actually has a lot of statements. And another one. For example, we prove that 1 plus 3 plus 5 plus 7 plus 9, those are the odd numbers. And we add the first n odd numbers. We add them together, we claim it's exactly n squared. And actually this is also contains a lot of statement. For example, when n is 1, you will get 1 is equal to 1 squared. That's true. When n is 2, so you just get first two, the sum of first two odd numbers is equal to 2 squared. N is 2. Remember, n is 2. You just add the first two odd numbers. When n is 3, you add first 3 odd numbers, you will get 3 squared. Right? N is 4, you add the sum of the first 4 odd numbers is equal to 4 squared. So for each different integer n, for each different natural number, you will have a different statement. Alright? So that's the statement based on the natural numbers. It works for all natural numbers. So how do we prove this type of statements? The proof depends on the following so-called the principle of mathematical induction. The principle of mathematical induction. Let's first check what it is. Suppose that the following two conditions are satisfied with regard to a statement about natural numbers. Okay, so what conditions? So two conditions. What conditions? Condition 1. And condition 1 says a statement, see, the statement is true for the natural number one. The statement is true for the natural number 1. This is a condition 1. Condition 2. The condition 2 says if the statement is true for some natural number k, it is also true if, then it is also true for the next natural number k plus 1. So if you assume this statement is correct for the k, you can prove, you can get that the statement is also true for the natural number k plus 1. With these two conditions, then the statement is true for all natural numbers. For all natural numbers. So this is the principle of a mathematical inductions. Okay? So you have to literally check the statement is correct for the number 1. And then you're going to prove that, assume for number k the statement is correct. How do you get k plus 1 is also correct for the statement? If you can prove those two steps, then by the principle of mathematical induction, we will say that the statement is correct for all the natural numbers. Okay, we will have several examples. And in the textbook, the author gave a very, very good illustration why we have this mathematical induction. So we use that dominoes, right? So we have a lot of dominoes. A lot of dominoes. Condition 1 means you're going to push down the first domino. Okay, push down means you're going to verify the statement for the first domino. Okay, and step 2, or condition 2, if the kth domino is down, if you place them properly, you put the dominoes close enough, the kth domino will intrigue the k plus 1's domino also down. K plus first domino is also down by your argument. By your argument here, it means by your by the distance you placed. Okay, if you can do this, then all dominoes will be down. All dominoes will be down. All dominoes will be down means the statement is correct for all the natural numbers. The natural number represented the position number of the dominoes. First implies the second implies third implies the fourth, and it's an automatic chain process. right? So this is a like illustration why the principle of a mathematical induction is correct. The second step is like you build a certain automatic chain. One will push to the next one will push to the next one. And the condition 1 means you have to start it. You have to push the first one, and then by this machine, you will the whole thing will be proved by the machine you have. All right. So let's see how we use this idea to prove certain statement involving the natural numbers. Okay, show that the following statement is true for all natural numbers and for all natural numbers n 1 plus 3 plus 5 dot 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 and plus 2 and minus 1 is equal to n squared. Okay, the sum of the first n other numbers is equal to n squared. Okay, let's see the proof. We have to verify two conditions. Condition 1, condition 2. We have to push the first domino. First domino for n is equal to 1. And let's check the left hand side. Left hand side, the first 1. Here is the first n odd integers. The first one odd integer. The left hand side is 1. And right hand side is n squared. N is a 1, so it's a 1 squared is equal to 1. So the left hand side is equal to the right hand side. The statement is correct. The statement is true for n equal to 1. Okay? And second, we will go to check the second condition. If the case domino is down, assume that the statement is true for k. So when n is equal to k, i.e. for n equal to k, the left side is equal to the right side. Statement is true, so it's a 1, just this k, 1 plus 3 plus 5 plus 2k minus 1. N is equal to k. 2k minus 1 is equal to k squared. All right? So assume the statement is correct for k. Now we want to verify. You see, it is also true for the next natural number k plus 1. If it is true or not, you are going to prove it. That is the main part of this mathematical induction. You must show it is also true for the k plus 1. Then for n equal to k plus 1, we want to know if it is equal to the left hand side is equal to right hand side or not. So for n equal to k plus 1, the left hand side, so far we still don't know if the statement is true for n k plus 1 or not. So you cannot set equality for n plus 1 at this moment. You can only study the left hand side and right hand side. Okay, left hand side becomes 1 plus 3 plus 5 plus, here n is a k plus 1, so the last odd integer is a 2 times k plus 1 and minus 1. 2n, n is a k plus 1. Okay? Let's simplify it. So it's a 2k plus 2 minus 1. So it's a 2k plus 1. Okay, so how do we show it is equal to the right hand side, or how do we get the computation? The thing is the following. So here, this is the first k plus 1 odd integers. First k plus 1 odd integers. And this is the first k odd integers. How do you get the first k plus 1 odd integers? You have first k and you add the next one, right? You have first, you see this is first 1, first 2, first 3. Whenever you increase the one index, you just add it from the tail. So this first k plus 1 odd integers is actually 1 plus 3 plus 5 plus up to 2k minus 1 and next 2k plus 1. This is the last one. So the preceding term is 2k minus 1. And this is the sum of a k odd integers. And the next one is the sum of a k plus 1 odd integers. You see? Let me see if you can read it. Oh. Okay, I hope you read it clearly. Okay? So by the hypothesis, we assume that the statement is true for k. So it means 1 plus 3 plus 5 plus up to 2k minus 1. By our hypothesis, this is equal to k squared. You see, this one is correct. You assume it's correct, so you can use it. And then plus the next one, 2k plus 1, the last term. All right? And well, it is a k squared plus 2k plus 1, and we know it's a k plus 1 squared. K plus 1 squared is exactly the right-hand side for n equal to k plus 1. So this is the right-hand side. Okay, so you do some computation, and based on your assumption, you show that if the statement is true for k, then by your computation, the statement is also true for k plus 1. So you build that automatic machine. Okay, you push the first domino. You build this automatic machine. You place the domino close enough. And then by the mathematical induction, the statement is true for all natural numbers. The statement is true for all natural numbers. So this is our first example of the mathematical induction. So you see here in this long proof, only this part is a tricky part. This part is tricky. First step, you just verify it for n equal to 1. In most problems, it's just a routine check. And the second step, you start from your assumption. The statement is true for k. You get the statement correct for k plus 1. This part, you have to do some algebra. You must show your intelligence and get the connection between k plus 1 to k. So for example, here we see that this is the first k plus 1 integers, and we just consider first k integers, then we can apply the assumption, and you simplify the sum of k first k odd integers and add to k plus 1, you get the k plus 1 squared. So this part requires some tricks or the ideas. Okay? Let's see the next. Show that 1 plus 2 plus 3 plus 4 plus n is equal to n times n plus 1 over 2. Let's try to prove it. the sum of the first n integers is n times n plus 1 over 2. Okay, proof. This is definitely a statement involving the natural numbers. So for n equal to 1, the left hand side is just 1, the sum of first one integer. The right hand side 1 times 2 over 2 is also equal to 1. So left hand side is equal to right hand side. The statement is true for n equal to 1. So you push the first domino. Assume that the statement is true for n equal to k. So assume the k's domino is going to be done. Assume it is the statement is true for n equal to k, i.e. 1 plus 2 plus 3 plus up to k is equal to k plus 1 over 2. So that's the case domino. And we are going to show it will push the k plus 1's domino down, k plus first domino down. So will it push the next domino down? We let n be k plus 1. We check the left hand side. You see, add up to n. N is a k plus 1, so you use parentheses to emphasize this is n. So we add first n plus 1 integers. First n plus 1 integers, of course, if you write the preceding term of a k plus 1 is a k. And this is the first k integers. And by the assumption, you know that the sum of the first k integers is k times k plus 1 over 2. Correct? And then you add the k plus first integer. And then you're going to simplify it. Here it has a k plus 1, here have k plus 1. You factor out k plus 1. Then this is a k over 2 and plus 1. So k plus 1. Here it is 2, k plus 2, right? So you find the common denominator. Common denominator is 2. So this is k plus 2. And the denominator is 2 is here. K plus 1. K plus 2, you write it like a k plus 1 n plus 1. Okay? So k plus 1 and then plus 1. It's a k plus 2. And then you can see this is n. This is n. So the right-hand side, when n is a k plus 1, this is exactly the right-hand side. K plus 1 times k plus 1 plus 1. This is equal to right-hand side. So the statement is true for n equal to k plus 1. The statement is true for n equal to k plus 1. All right? So it's like you really set up the automatic machine from the case n equal to k to the case n equal to k plus 1. Okay, then you are going to say that by the mathematical induction, the statement is true for all natural numbers. Okay? All right? Do you get any idea about it? Let's try more. Let's find one more. For example, let's see this one, the exercise 17 on page 969. They ask you to show that 1 times 2 plus 2 times 3 plus 3 times 4 plus up to n times n plus 1. It is equal to 1/3 n, n plus 1, and n plus 2. 1/3 n, n plus 1, and n plus 2. Okay, let's try to prove. For n equal to 1, the starting point, the first domino. N equal to 1, so you only have one term. The left-hand side is equal to 1 times 2 is equal to 2. And right-hand side, n is 1, so it's 1/3 times 1 times 2 times 3. 1, and then 1 plus 1 is 2, 1 plus 2 is 3. 3 cancelled, is 1 times 2 is 3. So the left-hand side is equal to the right-hand side. The statement is true for n equal to 1. Okay, then assume that the statement is true for n equal to k. So the kth domino will fall, i.e. 1 times 2 plus 2 times 3 plus up to k times k plus 1 is equal to 1/3 k, k plus 1, and k plus 2. And then let's examine the next domino for n equal to k plus 1. For n equal to k plus 1, the left-hand side is 1 times 2, 2 times 3, up to k plus 1 times k plus 1 minus plus 1, k plus 2. Right? The next one more term. This is a last term for n equal to k. Its next term will be the last term for n equal to k plus 1. All right. So we do some similar observation. We literally write the preceding term this preceding term. We'll just write the second last term. And this is exactly the left-hand side of the assumption. So by assumption, this is equal to 1/3 k, k plus 1, and k plus 2. And then plus k plus 1 and k plus 2. So you factor out k plus 1, k plus 2. And then this part becomes k/3 plus 1. Here you have 1/3 times k. So k/3 plus 1. And this is k plus 3/3. So we write it formally, it becomes 1/3 k plus 1, that's its first term. And then k plus 1 plus 1 is k plus 2, it's this second term. And then k plus 1 plus 2, it's the last term. And this is exactly the right-hand side. When I say right-hand side, it means the right-hand side when n is a k plus 1. The right-hand side when n is a k plus 1, it looks like this. So the statement is true. For n equal to k plus 1, you build this automatic machine. Then by the mathematical induction, the statement is true for all natural numbers. Okay, the statement is true for all natural numbers. All right. So this is on three examples. Mathematical induction is not only used to prove some equality, it can also show some inequality. Now let's see some inequality. Show that two to n is greater than n for all natural number n. Okay, so we're going to use mathematical induction to show this inequality, because this inequality also involves the natural numbers. Okay. Proof. For n is equal to 1, the left-hand side is equal to 2, and right-hand side is equal to 1. So the left-hand side is greater than the right-hand side. The statement is true for n equal to 1. Right? 2 is greater than 1. And then assume that the statement is true for n equal to k, i.e. when n is a k, 2 to k is greater than k. 2 to k is greater than k. All right? Then for n is equal to k plus 1. Okay, n is equal to k plus 1. Let's check the left-hand side. Left-hand side is 2 to k plus 1. Well, this one is different from the first few examples. The first few examples, we just write the preceding term, and we will see the first few terms, they can be combined, and then add the last term, everything will be solved. And here, there's only one term. There's no preceding term. So here, we're going to use some, not a trick, but we will see some observation. 2 to k plus 1 is 2 to k times 2. K plus 1. Power k plus 1 means you have additional copy 2. 2 times 2 to k is 2 to k plus 2 to k. 2 times 2 to k, it means you have 2 to k. Okay? So now we have 2 to k. But we know that what we are going to show. Okay, so we know that 2 to k is greater than k. This 2 to k is greater than k. So it's greater than k plus k. Okay, it's greater than k. This one is greater than k. This one is greater than k. So it's greater than k plus k. And k plus k, k is a natural number. K is, of course, greater than or equal to 1. You keep one k and you make another k smaller. It's greater than or equal to 1. Okay? So you see here, this term, you break it into two equal parts, and then each of them is greater than k. And then you reduce this k to be number 1. So you get this k plus 1. The k plus 1 is the right-hand side. So you get the left-hand side is strictly greater than, my bad. The left-hand side is strictly greater than the right-hand side. The statement is true for n equal to k plus 1. The right-hand side means the right-hand side when n is equal to k plus 1. You see, this strategy is totally different from the first few examples. All right? Okay, so you verify the first one. You assume it's true for k, and you prove it's true for k plus 1. Then by the mathematical induction, the statement is true for all natural numbers. N. Right? It's true for all natural numbers N. All right? Let's see another example. This is a problem 27. Show that 1 plus a to nth power is greater than or equal to 1 plus na, 1 plus na for a greater than 0. A greater than 0, a is a positive number, it's a fixed. So the changing part is n. So this is a statement involving the natural numbers. Let's prove. For n is equal to 1, when n is equal to 1, the left-hand side is equal to 1 plus a. To 1 is just 1 plus a. The right-hand side is 1 plus a. N is 1, 1 times a is 1. So the left-hand side is equal. Equal, of course, is also greater than or equal. It is included in this equal sign. So the statement is true for n is equal to 1. Okay, so always the first verification is not that difficult. It's almost trivial. Assume that the statement is true for n equal to k, i.e. 1 plus a to k's power is greater than or equal to 1 plus k times a. Okay, 1 plus k times a. Now for n equal to k plus 1, n equal to k plus 1. Okay, now let's try it. The left-hand side is 1 plus a to k plus 1, 1 plus a to the power k plus 1. And we do the similar trick like this. It is a 1 plus a to power k times 1 plus a. All right, we just separate it. We want this 1 plus a to k's power because here we know it. And this is a is greater than 0. This is a positive number. For the positive number, this factor times a 1 plus a, it will be greater than or equal to 1 plus ka. Okay, my bad. 1 plus k times a times 1 plus a. This first factor is greater than or equal to 1 plus ka, so we just put here. Correct? Okay, now let's multiply it. It's 1 plus ka, everything times 1, and plus a and plus ka squared. Ka times a, ka squared. And remember, k is an integer. A is a positive number. So this term will be greater than 0. Right? This term is greater than 0. So I drop this term. This term is greater than 1 plus ka plus a is a k plus 1a. K plus 1 times a. I just drop it. You see, this is the tricky point. Why do you drop it? Because if you drop it, 1 plus k plus 1 times a, this is the right-hand side. N is equal to k plus 1. This is the right-hand side. So you do prove that the left-hand side is greater than or equal to the right-hand side. So the statement is true for n equal to k plus 1. Okay, then by mathematical induction, the statement true for all natural numbers. It's true for all natural numbers. You see? See, this is a complete proof. And you will see that in these two examples, the strategy will be slightly different from the first three examples. When you just try to add a bunch of numbers together, and you possibly will use a similar strategy. You just consider the first few terms or some subgroup, and those some subgroup is exactly covered by the assumption n equal to k, and you add additional term and do something. And for these two, you have to keep some part. For example, here you keep one k, ka and a. Here you keep this k. You change it another part. Here you change k to be 1. Here you change ka squared to be 0. Drop it. So for this, the last two examples, they are more tricky than the first three examples, right? Okay, let's see the next example. Show that 3 to nth power minus 1 is divisible by 2 for all natural numbers. N. Okay, so given whatever integer n, that natural number n, this difference is always a multiple of 2. Let's prove it. For n is equal to 1, okay, now there's no left and right hand side. We just verify. N is a 1, it's a 3 to 1 minus 1, it's a 2. Of course, 2 is divisible by 2, right? 2 is divisible by 2, so the statement is true for n equal to 1. And assume that the statement is true for n is equal to k, i.e. 3 to k minus 1 is divisible by 2. Okay, so 3 to k minus 1 is divisible by 2. Now for n is equal to k plus 1 for the next integer. For the next integer, we will get a 3 to k plus 1 and minus 1. Right? 3 to k plus 1 and minus 1. It's similar to the 2 to n plus 1, 2 to k plus 1. So it's a 3 times a 3 to k minus 1. We try to manipulate this 3 to k plus 1. So this additional sum on the 1 means you have additional factor 3. And okay, so now let's see. I know 3 to k minus 1 is divisible by 2, but here I don't have 3 to k minus 1. So I'm going to generate 3 to k minus 1. I do subtraction by 1 inside it. Actually, you multiply 3, you subtract 3. Subtract 3, you add 3. And this minus 1 is copied. Okay? You see what I do? I subtract 1 inside times 3. It's equivalent to I subtract 3. Subtract 3, add 3. I balance it. And then subtract 1. It's from the previous term. Okay, so it's a 3 to k minus 1. 3 minus 1 is 2. Okay, now we can do some argument. 3 to k minus 1 is divisible by 2. So is 3 times 3 to k minus 1. Right? So this one is a multiple of 2. Times 3, it is still multiple of 2. This is still multiple of 2. And so is 3 times 3 to k minus 1 and plus 2. So this is a multiple of 2. You add 2, it's a still multiple of 2. Right? You add 2, just get an even bigger even integer. So the statement is true for n equal to k plus 1. So here we do show that so is this. It means this number is a multiple of 2. It's divisible by 2. So the statement is true for the integer n equal to k plus 1. Then you are going to say that the conclusion. So by mathematical induction, the statement is true for a natural number. All right? So this is another different example. In this example, there's no left side and right hand side. It's just have a real statement. You're going to show that this statement is correct for all natural numbers. See? Okay, let's do more. Let's try 20. Exercise 20 on the same page, 969. It says n cubed plus 2n is divisible by 3. Wow. Okay, let's try. For n is equal to 1, it's a 1 cubed plus 2 times 1. This is a 3, right? So it is divisible by 3. The statement is true for n equal to 1. Then assume that the statement is true for n equal to k, i.e. k cubed plus 2k is divisible by 3. Okay, so then for n equal to k plus 1, n is equal to k plus 1, let's try it. K plus 1 cubed plus 2 times k plus 1. All right, let's expand it and check it. K plus 1 cubed. If you just do the multiplication, you will see it is k cubed plus 3k squared plus 3k and plus 1. And the other part is 2k plus 2. All right, just expand it and let's try to simplify. See here, this one, we're going to use this as a group, k cubed plus 2k. This combination is divisible by 3. So I have k cubed, I have 2k. I'm going to put them together. This is a multiple of 3. And then 3k squared. 3k here, 1 plus 2 is a 3. So you factor out 3, you will get k squared plus k plus 1. This sum is a 3, so that's why you can factor out 3. All right, so now let's do the argument. K cubed plus 2k is divisible by 3. Of course, 3 times k squared plus k plus 1 is divisible by 3 because it has a factor 3. So this sum is divisible by 3, right? So the first summand is divisible by 3. Second summand is divisible by 3. So the sum is divisible by 3. So the sum is literally this case 1n is k plus 1. So the statement is true for n equal to k plus 1. Again, there's no left side, right hand side. It's just a real statement. So you prove the case is true for n equal to 1. You assume the statement is true for n equal to k, and you show that it is true for the n equal to k plus 1. Then by mathematical induction, the statement is true for all natural numbers. All right, that's the complete proof. Okay, so you see the ideas or the steps, they are very formatted. So there's no memory. What's the next step? So basically just step 1, a step 2, and a step 3. The verification for the first step, for the n equal to k, assumption for n equal to k, the verification for n equal to 1, the assumption for n equal to k, the proof for the n equal to k plus 1 based on n equal to k. And then you just write down the statement, result, conclusion. But for the third step, when you try to get the proof for n equal to k plus 1 based on the case n equal to k, it may be tricky. It may be a little bit tricky. So you have to do the problem by problem, and you try to fill your own tricks. There's no way to say what is this trick, what is that trick. But if you have a sum of the integers stuffs, you possibly will use a similar trick. For the n plus 1, k plus 1, you just reduce it to the case for the k, and you add first the k terms together and then add the final term. Okay, that is the regular strategy. But except that, there's no fixed tricks. You have to do it one by one. Okay, so do the exercise. Send me email if you have questions. Thank you.